Good afternoon, respected participants, esteemed colleagues, and distinguished guests. Today, I, Dr. Isha, wants to extend a warm and heartfelt welcome to all of you for Day 3, Session 2 of this Faculty Development Program on recent advances in renewable energy technologies. In this context, today's FDP is of immense significance as it provides us with the opportunity to not only gain insights into the latest technological developments, but also to engage in discussions that can help us bridge the gap between research and practical application. We are honored to have with us Mr. Sunil Kumar. Welcome, sir.
Good afternoon, Isha, and good afternoon to all the participants.
He is Senior DGM, New and Renewable Energy Business, BHEL, New Delhi. He had completed his mechanical engineering from IIT Kharagpur and postgraduate diploma in management from IMI New Delhi with ESCP, Europe, Paris, and Berlin. He has expertise in solar power plant, business development, system engineering, and project management. He had executed several projects in nuclear power plants, SAP, enterprise resource planning. He has associated with Tata Infotech Limited from 2001 till 2002 and BHEL since 2002. He has more than 22 years of experience in the field of energy technology. Throughout this program, Mr. Sunil Kumar will guide us through the innovations in market scenario and overview of solar based power plants. We are sure that your insights will not only inspire us but also empower us to integrate these advancements into our teaching, research, and professional practices. I encourage everyone, all the participants, to engage actively during the sessions, ask questions, and foster meaningful discussions. Once again, welcome you, sir, and I'll take over you. So please present your presentation.
Thank you, Isha. Uh,
Thank you,
at
sir.
the outset, I thank Gautam Buddha University for having me and giving me an opportunity to share actually my experience in the field of solar industry in marketing and engineering and project execution. As Isha told that presently I'm working in BHEL. I'm Senior Deputy General Manager, New and Renewable Energy Business in BHEL Lodhi Road. And my presentation will be basically on the market scenario and overview of the solar-based power plants. And we will touch upon the trends in solar power plants and in technologies, which are the technologies which are coming up, like ground-based, floating solar. Those parts I'll cover. And I request that all participants feel free to stop me in between if they have any query and ask me any questions in between also. So uh, this is not very big presentation. Um, I'll be covering basically one slide on about BHEL, one slide on market scenario, then some basics of the solar photovoltaics. I hope the presentation is visible to all the participants.
Sir, yes, your presentation is visible.
Thank you, thank you. And I'll touch upon the solar power value chain, basically from silica to electrical energy, how we convert it. Like from silica, we make polysilicons, then wafers, then solar cells, then solar panels. Then we integrate all solar panels uh, in a solar plant, and how the solar plant generates the power and it feeds to the grid and the households. And I'll touch upon floating solar power plant also, which is a new trend in industry because solar plants then usually requires a huge land bank. Uh, it requires around 4 to 5 acres of land for 1 megawatt of power plant. So in India, as on date, around 100 gigawatt solar plants, almost 1 lakh uh, megawatt solar plants have already come up. So there is a scarcity of the land in many parts of the country. So floating solar is also a new trend which is coming up. So I'll touch upon that also, and I'll share with you from solar, from sun, how the energy comes, how it converts to uh, electrical energy, and what are the losses happens in between, uh, and how power is transmitted to the grid. So this is my presentation's content. If you talk about the BHEL, actually, we are central public sector undertaking. We comes under the Ministry of Heavy Industries. We are Maharatna Public Sector, and BHEL is the largest uh, engineering and manufacturing enterprise in the field of energy and infrastructure in country. Uh, BHEL, as on date, has installed coal-based thermal power plants, 465 sets, which comes to around 135 gigawatt. And similarly, for the gas power plant, diesel-based power plant, nuclear power plants, hydro plants, and solar plants. So BHL, if you see uh, in country, whatever thermal plants are there, or whatever hydro, thermal, or nuclear plants, more than 60% of thermal plants are equipped with the BHL supplied uh, boilers, turbines, generators, uh, these things. And as on date, we are having a workforce of around 27,000 people. And out of 27,000 people, around 9,000 are graduate engineers. So it's a big pool of engineers in BHU, which takes care about engineering, procurement, construction, site services, uh, operations, that part. So this is about BHL. If we come to the market scenario, how the market is there in country for solar, as far as solar is concerned, government is uh, pushing solar installations through various schemes and incentives, and they have set up the target of 365 gigawatt. It means 365,000 megawatt of the solar power plants. Government is targeting by year 2032, and as on date, uh, December 24, 98 gigawatt of solar power plants were already set up in the country. Another 83 gigawatt of solar power plants are already in various phase of installations. So this is the scenario. And if you see the majorly three states, Gujarat, Rajasthan, and Andhra Pradesh, they contribute largely for the solar power plant. The reason is obvious, because solar radiation is very high in in these states. So investors and power plant developers, they find these states attractive because they'll get the higher generation and they get the higher revenue. If you see the government driving forces, what are the driving forces? As far as solar is concerned, uh, as I told that around 365 gigawatt of installations will be there in the country by 2032, and government is developing the solar parks. Like if I'm an invest developer, I want to develop a solar plant. So along with the solar plant equipments, I need land, I need transmission infrastructure, uh, and I need I had to coordinate with the landowners. So this part government is facilitating, and they are developing the solar parks in different parts of the country. Government has identified already 40 gigawatt of solar parks, which they are developing. Further, I think my all participant might have heard that recently government has announced scheme for residential household also, like 1 crore rooftop solar power plants, solar systems uh, will be, or 1 crore houses will be powered with the solar uh, rooftop solar. This is called the Pradhan Mantri Surya Ghar Muft Bijli Yojana. So in this scheme, what you can do, you can put up the solar plant on your roof. You can connect that solar plant to the grid. Daily basis, you can inject the electrical energy to the grid, and at the end of the month, when your electricity bill comes, so whatever electricity you have pumped into the grid, that will be minus. So this is a one incentive which government is giving. Further, government is uh, uh, allowing or facilitating the power purchase agreement for 25 years. It's basically the uh, between the developer and discoms. They interact. There is an agreement where developer develop the plant. They sign the agreement with the discom for the 25 years. So 20 up to 25 years, discoms are bound to buy the power from the developers at the agreed rates. Further, if you see the generation cost of solar plant has come down drastically in last 4 5 years. The generation cost of solar of electricity, it means per unit generation cost from the solar plant is around 2 rupees 60 paisa, which is much cheaper than the uh, your diesel. Diesel is costing around 15 to 20 rupees. Because we are many people are maybe staying in the apartments, and whenever DG is set on your apartment association or the maintenance, they are asking around 20 to 25 rupees per unit from you. But this is the in case of the diesel. But if you see the solar's tariff or solar's generation cost is just 2 rupees 50 paisa. So it is making, or these are the factors which are driving the solar industry in the country. Uh, and if if we come to the basics of the solar photovoltaic, basically there is a two types of solar. I have gone through the uh, your 1 week's program. What uh, you all participants are being shared. I think in that there was a solar thermal also. So I want to touch upon a little bit here. Like there is a difference between the solar photovoltaic and solar thermal. Solar photovoltaic is basically converting the sunlight directly to electricity. So sunlight falls on the solar panel, and the other side of the solar panel, there is the electricity. So there is no other equipment, or there is no other components in between. Uh, in case of solar thermal, which generally very simple example is our roof may be having the solar thermal, which is used to uh, heat the water. And solar thermal power plants, if we talk about the solar thermal power plants, what they do, they convert the sunlight to heat, heat is converts water to steam, and that steam is used to run the turbines. Some sort of the conventional power, but only one thing is there, that instead of burning the coal in boilers, we are using the sunlight to heat the or to make the steam. So these are the two basic difference between the solar photovoltaic and solar thermal. If you come to the solar photovoltaic basics, basically I told that it is a direct conversion of sunlight to electricity. And what is the source of uh, that energy? That energy is basically the sun. So actually, all living beings, all source of energy on Earth is basically coming from the sun. And we all know that at the core of the sun, there is a nuclear reaction is happening, where hydrogen fuse and they make the helium. And in this fusion, there is a fraction of mass which is not converted to, or which comes out, uh, which remains out of the atom. Basically, this is the fraction of mass which uh, comes out. So this fraction of mass is converted to the electricity. So this is the famous Albert Einstein equation. Like this mass is mc square, energy is mc square, where the fraction of mass and the c is the speed of the light. So this is the source of life and energy on the earth. So if you see the solar photovoltaic, what is happening? Uh, Solar light is falling on the solar cell. Actually, this diagram is solar cell. Sunlight is falling on the this solar cell, and this is getting converted directly to the electricity. So it is a small animation. Uh, just it will show how it is happening. Like sunlight is falling on the top of solar cell. Uh, Actually, this solar cell is a PN junction, because to have the photovoltaic effect, it is a must that you have the PN junction. If there is no PN junction in silicon, no electricity will be generated. No photovoltaic effect will have. So sunlight is falling on the top, which is a n dop. N dop means there is a phosphorus doping on the top, and electrons are in excess. So when electrons are in excess and sunlight is falling on that, so those free electrons comes from the conduction, from the valency to the conduction after gaining the energy from the sunlight. So when continuous light is falling on the n-doped surface, so lot of electrons are coming. Lot of electrons are coming on the uh, surface in the conduction. So it creates the potential between top and the bottom surface. So if you connect the wire from top, which is the blue color, which I have shown in the animation, once you connect the top and dop to the p dop backside, so it creates the it because potential is already there, because a lot of electrons has come on the top. So potential is already there. Once you connect it to the your n dot to the p dot, electrons starts flowing, and that is the current basically. So this is a very fundamental what is happening in the cell, at the cell PN junction, what is happening. And if you see these cells, solar cells, they never run out of the electrons, because ultimately whatever is coming from the top, it is going to the backside, and again then it is getting diffused to the n type. As I told that PN junction is mandatory, or it's a must for having the photovoltaic effect. one example, one animation I have shown here, like there is no PN junction. It's a pure silicon wafer, where the pure silicon purity is 99.9999, which is called the 9N basically. It is such a high purity silicon wafers are used in uh, solar industry. So there is no this animation shows because there is no PN junction, so no electricity is flowing. If we come to solar PV value chain, like from silica to electrical energy, how we are converting into the full solar photovoltaic value chain. Actually, it starts with the quartz. This is the quartz. Quartz is basically the silicon dioxide, which is uh, it's abundantly available in sand. And if you see the beach sand in the seashore, so there is the rich source of the silica. Uh, so from this silica, what we do, we convert it to metallurgical grade silicon by the chemical process. It is converted to metallurgical grade silicon, where the purity of silicon, so this is a metallurgical grade silicon, where the purity of the silicon is about 98%. So this 98% is of no use for the solar industry or for the semiconductor industries. This is generally used in the aluminum uh, industries and steel industries. So, but in semiconductor industries and uh, solar industry, this purity is of basically of no use. This is a very low purity silicon. So from there, what generally is done, it is converted to the uh, higher purity silicon, which we call it the polysilicon. So this is the polysilicon phase where the purity comes to 99.99. This is N 9N basically uh, purity, and this is used in the solar industry. But for the photovoltaic industry, uh, this is sufficient. But for semiconductor industry, where the purity is required very high level, so the purity level for the semiconductor industries to make the ICs and other things is basically 12N. So this is N 9N purity. So for semiconductor industries, the silicon purity is 12N. So from polysilicon, it is casted to the ingots. Basically, this polysilicon does not have any crystal structure as on when it comes to the when it we convert it to the silicon ingots, the crystal structures are formed. So there are the two type of silicon st- structures. One is a monocrystalline and another is a polycrystalline. That we will difference we will see in the next slides. Uh, then from these ingots, we cut uh, these ingots and we prepare the silicon wafers. So this small size is a silicon wafer. The size of this silicon wafer is 182 by 182 mm. So that is the size, and thickness is around 150 microns. So thickness is very small, just like human hair. That is a small thickness. And from, as I told that this wafer does not produce any uh, or they it no photovoltaic uh, uh, things happen on silicon wafers. So what we have to do, we have to make the PN junction and make the circuit so that the whatever electrons are generating on the n dot surface, those can be they can be given a circuit to go to the P side. So these lines which we are seeing on solar cells, these are the silver lines which provides the circuit to the uh, free electrons so that they can go to the P side. And these solar cells are assembled together, and solar panel is made. This solar panel rating or the rating is around 540 watt. So this single solar panel can produce 540 watt of electricity power when it is exposed to the sunlight. So from these solar panels, we construct the solar power plants. So this is a photograph of one solar plant where multiple solar panels are connected. They are connected in a series and parallel combinations, basically to get the desired voltage and desired current. So these are connected into the series and parallel combination, just like battery. So this is a overview of solar PV value chain. What happens from silica to electrical energy. So this solar plants generates the electricity. Now we go in a little bit detail. If we talk about silica ore, this is the first part. The silica ore is basically is a silica. This is a silicon dioxide, and this is plenty available in Earth. In Earth crust, it is the second most abundant uh, material we can say on the Earth crust. And the beach sand consists rich silicon dioxide. So from that we convert to the metallurgical grade silicon, and this is a simple chemical process. What we do actually, we burn it with the charcoal at the high temperature. The temperature is very high, around 1500 to 2000 degrees centigrade. Silica ore is melted, and we get the silicon here. So carbon dioxide is generated, and we get the silica. If we see the source of these uh, silica in the world, China is producing almost 60 to 70% of metallurgical grade silicon. Apart from China, Brazil, US, Norway, France, Australia, Germany, and India, some part India is also making. And If you see per megawatt in solar plant, per megawatt solar plant will require around 7 ton of metallurgical grade silicon. Uh, from quartz, we have come to the metallurgical grade silicon. Then we process this metallurgical grade silicon to polysilicon, which is a higher purity of silicon. Uh, there is no production in India for this high uh, grade or high purity silicon. And the leaders are China. China is producing 80% of world's polysilicon. Apart from China, there is the Korea, US, and Germany who are producing it. Uh, from polysilicon, as I told, that we make ingots, and from ingot we cut the ingots and we make the wafers. So these are the another process. And as what I mentioned, like crystals are formed, or crystals can be formed in two ways. One is the monocrystalline and one is the multicrystalline. So this is the photograph of monocrystalline, where all the uh, crystals or the lattices are in the same directions, either in 110 or maybe 101 or maybe 11. So all crystals will be in the same orientation. But in case of the multicrystalline, there is also a pattern, uh, but pattern or the structures are there, but it's not a continuous structure. So in some part of cell, there may be 110. In another parts, in the same cell, On the adjacent or the at the boundary, at the grain boundary, there may be another structure. So in monocrystalline, the crystals are in the same orientation. In multicrystalline, crystals are there, but in the different orientation. So again, here the China is a leader in production, and apart from China, Korea, US, and Germany they are making. India is having the zero production capacity as on date, but government is giving some production link incentives, which we call it the PLI, to some of the uh, manufacturers. So hopefully in India also, maybe I think 2 3 years, there may be the manufacturing facility for ingots, polysilicon and ingots. If we see the photograph, how does this monocrystalline and multicrystalline looks? This is the monocrystalline cell where the crystals are all crystals are in same orientation, and it has this little bit blackish color. But if you see the multicrystalline, it's a clearly showing that crystals are there, but they are not in the same orientation. At the different part of wafer silic cell, there is a different structures are there. So we can see clearly from the photographs also, like this is monocrystalline, this is multicrystalline. Then what we do, these wafers are doped to form the PN junction. And as I told, the front is printed with the silver paste so that the electrons, whatever electrons are generated in the photovoltaic effect, those can be collected or those can be given a circuit to pass on to the next cell and to pass to the circuit. And this I've already shown actually, this photograph. And this cells comes in a different size and efficiency. Like right now 182 mm, as I told that 182 by 182, this is the most prominent size of silicon wafer or silicon cell as on date. The thickness is around 170 micron meter, which is the thickness of human hair actually. And the next size which is coming up in the industry will be the 210 mm. And efficiency, if you see the efficiency of solar cell, the efficiency means whatever sunlight is falling on the surface of uh, solar cell, how much that energy is getting converted to the electricity. So that is the cell efficiency. So as on date or presently, around 22 to 24% is a solar cell efficiency. It means whatever sunlight or sun energy is falling on solar cell. So out of that energy, 22% is getting converted to electricity. So this is a very simple formula, what we can see, how the efficiency is calculated. Um, like if you take the size of one cell, 182 by 182 mm size cell, this generally gives 7.5 watt output. So, and whatever sun radiation is falling on that cell, it is calculated in terms of the watt per square mm or maybe watt per square meter. So, on this uh, cell, this much energy is falling, 0.001 watt per square mm of energy is falling on the solar cell. And this is the area of one cell. So The area comes to 33,124 square mm. Once we multiply this area with the energy falling per square mm, so we get the this much solar power, or this much solar power is falling on a solar cell, which is around 33 watt. So 30 at this solar radiation level, around 33 watt of power is falling on this cell. And output, how much we are getting? Output we are getting 7.5 watt. So the efficiency is basically the output of solar from the solar cell, and the input. Input means whatever sunlight is for sun energy is falling on this cell, and the sun. This is the 7.5 by 33.124. So this comes to around 23%. So this is the way how we calculate the solar cell efficiency. So this has been the trend since 2010, how the efficiency of the solar cell has improved. A lot of research are happening in China, Germany, Singapore, Australia, and US. So if you see around 2010, during 2010, the efficiency of the solar cells used to be 13 to 14%, so which has uh, developed last 9-10 years. And as on date, if you see, it is around 22%. Almost double efficiency has been achieved in industry. So from these solar cells, we connect the solar cells to form the solar panel. And depending on the panel wattage, like what wattage of panel we want, so we can connect the number of cells, because we know now that one cell gives the output of 7.5 watt. If we connect 72 cells, we will get 540 watt peak. If we connect 36 cells, then we will get the around 270 watt peak. So this is the how we decide that how many numbers of cells to be connected to make a panel. Now these panels are connected in series and parallel combinations, series and parallel combination, to get the desired output in terms of the voltage and wattage. So if you see, these are the solar cells, and like solar cells are assembled to solar panel. This is just to show that what are the components are there in the solar panels. Like one is the solar cell. Over that we have the glass. Below we have the Tadlar film. It is a polymer sheet, and we can have the glass also. Nowadays, actually, double glass panels are also coming, where the top is also glass, and bottom is also the glass, which is called the transparent panels. Now, if we come to uh, solar-based power plant, actually, so far we have uh, covered basically what is the value chain of solar photovoltaic, like from silica. This is the silica. From silica uh, to energy, how we are converting from the silica to electrical energy. Now, if you go to the specific to the power plants, like at this level, so what are the component in the solar power plant? Uh, if you see like solar plant rating or capacity, when we say what is the rating of a solar power plant, basically we define in terms of the AC capacity. Whenever we say 100 megawatt solar plant, or 20 megawatt solar plant, or 50 megawatt solar plant, basically we are defining the AC rating of the solar power plant. And the AC rating of the solar power plant is the sum of all inverters, basically. How it is coming? Just to show, yeah, uh, there is a solar array, which basically solar panels produce the DC power. So though the series and parallel combination of solar panels are arranged in such a way that we get the very high power from the solar array. This is of the order of around 1.25 uh, megawatt. So that power, full power comes to the inverter, and inverter converts that power to the DC power to the AC power. So when we were saying that the rating of solar power plant, it is basically the sum of the rating of all inverters. Suppose there are the 20 inverters of 2.5 MVA which are connected in a solar power plant. So we can say that the efficiency or the rating of the solar power plant is 50 megawatt, because there are the 2.5 MVA inverters are there of 20 numbers, and total AC power comes to the 50 megawatt. So this is the way how we define the rating of a solar power plant. And sometimes we mentions the rating of solar power plant as megawatt peak DC also. Along with the megawatt AC, we mentions the rating of power plant as megawatt DC also. So this is basically the sum of rating of all solar panels. AC is basically the sum of rating of all inverters. And when we say the DC capacity of solar power plant, it is basically the sum of rating of all solar panels. So, for example, in a 50 megawatt power plant, suppose we are installing 92,600 solar panels of rating 540 watt peak each. So the output also comes 50 megawatt peak. So, but one thing which we can uh, note down here, like solar panels, 92,000 we are mentioning because the rating is coming 50 megawatt, but we can increase the solar panels on the DC side. Inverter rating we can keep 50 megawatt, but solar panels or the DC power we can increase. So it can be 60 megawatt peak, it can be 70 megawatt peak also. So this is the how we define the solar power plant rating or capacity. Whenever we say the 50 megawatt AC means it's a sum of rating of the all inverters. Uh, Basically, there are the basically four types of solar power plants which we see. One is the ground-based solar power plants, means uh, plant is erected on the ground. Like this is a photograph of ground-based solar plant power plant where all the panels are installed on the ground only. Then there is a rooftop solar power plant where the panels are installed on the rooftop. So it is a type of plant is basically with respect to where we are installing the solar panels. There are some canal top solar plant also, like on the canal we can put the solar panels. And new trend, as I told, that it is a floating solar power plant where the panels uh, we can say deployed on the water bodies. This is the one photograph. This is a 100 megawatt solar power plant basically. It is the AC rating is 100 megawatt and DC rating is 145 megawatt. This solar plant is at NTPC Ramagundam, Andhra Pradesh. So this solar plants covers the area of 500 acre. So over the 500-acre water body, the solar panels are installed. So this is the floating solar means all panels are deployed on the water bodies or the floating. The panels are floating. That's why it is called the floating solar power plants. Uh, Around 4 to 5 acre of uh, land is required per megawatt of solar power plant. This is the land requirement. And one important thing is because if you are seeing that all panels are inclined, no panel is on horizontal or the totally vertical. So panels are inclined. So there is a principle basically at what angle the panel should be inclined. It depends on the latitude of that site. What does it mean? If we are in Delhi, actually we are having around 30-degree latitude here. So the panels will be inclined 30 degree with the vertical. In equator, there is a 0 degree latitude. So panel will be fully horizontal. They'll, and if we suppose we go to the uh, Australia side, like other hemisphere, the panel will be based on the latitude, but the direction will change. Like in India or northern hemisphere, the panels are uh, panels always face south, and angle is equal to the latitude. So this is thumb rule basically, or the principle like uh, angle is equal to the latitude and panel face the south. And when we are in the southern hemisphere, we have to face the north. The idea is basically to get the maximum sunlight. Uh, and the sun energy, whatever sun energy is coming from the sun, it is calculated in terms of the global horizontal radiations. We call it the GHS. This is the quantum of solar energy which we are getting in different different parts of the country. Like the Gujarat, Rajasthan, and Andhra Pradesh, they are the highest uh, l- uh, level of food radiations is there, and that is around 2000 kilowatt hour per meter square per year. So this is the measure. Like on a square 1 square meter area in a year, we'll be getting around 2000 units of solar energy, not the uh, electrical energy, because electrical energy is derived from here, it will be converted, but the solar energy will be the 2000 units per meter square per year we will be getting. Similarly, in Delhi, UP, Punjab, and this our this belt, the uh, solar energy is less because of the um, rainy season, rainy period, and the during winter also, the solar radiations is very low. From a solar power plants, typically we get a generation of around 22 lakhs unit of electricity we get per year from a solar power plant, from a 1 megawatt solar plant. And the efficiency or the effectiveness of a solar power plant, we measure in terms of the capacity utilization factor. This capacity utilization factor is basically the plant is available, my plant 1 megawatt plant is available, but this 1 megawatt power plant cannot produce uh, 1 megawatt 24 hours in a day. because sunlight is available only from 6 a.m. in the morning to maximum 5:30 or 6 p.m. in evening. So during that period only, I'm getting the uh, sunshine. My power plant will also work during that time only. So generally, the capacity utilization of a solar power plant is in the range of the 24 to 25%. What does it mean? That in a day of 24 hours, only 24% time my plant is working on an average. Other times it's not working. So this is the basically the capacity utilization of the plant. This is the graph which shows how electricity is generated or how it is graphed on a hourly basis in a day. And if you see the cost of the solar power plant, the cost of the solar power plant is around ground-based solar power plant is around 3.5 to 4 crore per megawatt. Uh, Earlier, the price has come. This price has come down. Earlier, the price used to be very high. If you see during the 2010, 1 megawatt solar power plant used to be around 13 crore per megawatt, and in 2015, the the cost used to be around 6 crore per megawatt. But now the cost has come down drastically. One basically the reason is the cost of solar panels has come down. Earlier, the cost of solar panel used to be very high. Now the cost of solar panel has come down because of the mass manufacturing in China and other parts of the world also. Floating solar power plants are a little bit costly. The cost of floating solar power plant is around 4 to 4.5 crore per megawatt because they use the floaters, and the floaters has to have the buoyancy basically. So there is a special uh, blow molding is used to form these floaters. Further, anchoring and mooring is also needs to be done for floating solar. Otherwise, floating solar plants may like disorient or may get displaced because of the water waves. So it has to be anchored and moved so that it remains intact in a water body. Similarly, the rooftop solar power plant cost is very low, lowest among all type of solar power plants because it's a very simple. In the roof, you can just put the structure. Over that one of panels, very small rating of inverters, and no transformer is needed. So this is a very simple system. So the cost is also not very high, around 3 to 3.5 crore per megawatt is a rooftop cost. This is the cost of the solar power plant. But if you see what is the cost of energy generation from the solar power plant, so it comes to the typically around 2 rupees 60 paisa, which I told in the beginning also. Like from DG sets, the cost of generation of electricity is around 20 rupees, 15 to more than 20 rupees only. But from the solar power plant, the cost of electricity generation is just 2 rupees 60 paisa. And float from the floating solar, it may be 2 rupees 80 paisa or 3 rupees. As the cost of power plant has come down, it can be seen in the solar cost of generation also. Like in 2010 or 12, the cost of electricity generation used to be in the range of the 8 to 10 rupees, which has now come to around 2 rupees 60 paisa, 2 rupees 70 paisa. So this is the range which is available nowadays. So, but definitely the cost of electricity generation depends on uh, the location of the power plant. If the my power plant is in Rajasthan, the cost of generation will be less because I'll be getting the more generation from the same power plant. And if power plant, same power plant, if I install in, for example, in hilly regions or maybe northeastern region or maybe um, our Haryana or maybe this side, the cost of generation will be higher. So this is basically when we talk about the solar power plant, what are the terms we generally come across. So I had tried to explain uh, the solar power plant based on the terms we generally use, like plant rating, type of plants, what is the area needed, angle of inclination, why we do the inclination, why we can't put on the horizontal. Because the idea is basically to get the maximum sunlight. And we'll get the maximum sunlight when we face the sun. So in northern hemisphere, we face the sun by putting the panels on the southern side. And if you're on the southern hemisphere, like in Australia, we have to put the panels on the northern side. And the angle is the latitude of the site. So now if you see uh, what is there in a solar power plant, if you see the what are the components are there. So basically solar power uh, from the array, it is produced as a DC power. So this DC power goes to inverters where it get inverted to AC power. But this AC power is also uh, voltage is very low, like 415 or 430 or maybe I think 500 volt, depending on the inverter type. But generally these power plants are grid-based power plants, so these has to be connected to the grid. Power has to be connected to the grid, which is shown in this small diagram. Like solar array, they produce the DC power. This DC power is converted to the AC power by the inverters, and this AC power is uh, injected to the grid, but the voltage level of the grid is not 415 volt actually. This is generally 11 kV, 33 kV, 66 kV, 132 kV. So that is the high voltage level. And from the inverter, we are getting just 415 volts. So in between, we have to have the inverter, these transformers. So this is the flow diagram. Like AC power comes to inverter. This power converts to the uh, DC power comes to the inverter. This power converts to the AC power, and these power uh, step up from 415 to 33 kV or 11 kV as the desired output, and then it goes to the tariff grid. So these are the components of a solar power plant. Like these are the panels. As I told that these are the series parallel combinations we do in a solar array to get the desired voltage and an output. So this is the series parallel combinations. And for a typical 100 megawatt solar power plant, such type of panels are installed. Around 2 lakh panels are to be installed to get a 100 megawatt uh, power. And these are the mounting structures over which the panels are mounted. These are the civil foundations. Uh, these are the foundations which goes as deep as 3 meter in the ground, and the diameter of this is around 30 centimeter. It basically depends on the soil bearing capacity of the land where it is being installed. If soil bearing capacity is very good, so it can be 1.5 meter below ground level. If the soil bearing capacity is not there, then it go as I 3 and 4 meter also. These are the cables which, because power is produced, so this has to be uh, transported, or this has to be transmitted to inverter. So from there, that it goes to the inverter rooms. So these are the inverter room. So these are the inverters where the all DC power comes and get converted to the AC. And from these inverter rooms, there is the transformers which converts the uh, AC power of low volt to high volt, and it dispatched, or it is injected to the grid. If you see, this is the ground-based components. If you see the floating power plant, in floating power plant, what generally we have the solar panels. These are the solar panels. Those solar panels are installed on these floaters. These are the gray colors are the floaters over which the solar panels are installed. From there, it comes to the inverters. These are inverters. These inverters are also sometimes the floating inverters only. Uh, these are the concrete blocks over which inverters are there, and from that the power comes to the transformer and get uh, transmitted. So if there we are seeing that these are the mooring lines, like these are the connecting rocks basically, because uh, these a full assembly of solar panels has to be intact at its place. So this is possible only when we bind it with the ropes. So these ropes is basically called the mooring lines, and these are anchored to the ground so that it does not it gives a support to the uh, these modules and the floaters. So these are the some advantage of why we are. I mean, this is a new trend. Why floating solar is so popular nowadays, because it basically conserves land, which is a premium resource nowadays, and we get higher output also in floating solar due to the cooling effect. Actually, silicon has the uh, property. It has a negative temperature coefficient. As the temperature goes up, uh, the photovoltaic effect comes down. So higher the temperature, lower is the output. So in floating solar, we have the low temperature because of the cooling effect of the temperature water. So the efficiency is also high in case of floating solar. Further, it conserves the irrigation and water, drinking water from the evaporations. So it has been studies are there, like about 1 meter, 1 mm of water surface is saved by the floating solar. Once we install the floating solar, about 1 mm of water evaporation from the surface we can save. So in a year, it comes to around 30%. Um, then this is the it does not have any threat to the aquatic life, this floating solar, because all the components which are made like floaters, uh, solar panels, or inverters uh, which also floats on water. These are all they are free of the contamination. They don't contaminate the water. So this is the one photograph of uh, floating solar, 100 megawatt floating solar. This is installed by BHEL in NTPC Ramagunda location. So we were saying that anchoring, basically, this is the anchoring, like mooring lines we anchored. This is basically anchoring is done through the generally done through the dead weight. So this is the dead weight, like 8 ton dead weights are used to anchor the uh, full floating system. And This is the floating platform for equipments. This is the concrete block, which is a hollow concrete block, so that there is a sufficient buoyancy is there. And over this concrete block, uh, all electrical equipments like transformers, inverters, SCADA panels, switchgear panels, all electrical equipments are mounted on these platform only, and these platform also anchored and moved to the ground. And the life of design life of these solar power plants is around 25 years. So for 25 years, keeping in mind of that these has to float for 25 years, it has they are made uh, accordingly. So this is about the floating power plant. So I think more or less we have covered uh, the presentation. So now just we come to the last. This is the last slide. Yes, this is the last slide, which we where uh, I wanted to show that how energy is getting converted from sun to grid. How it is happening? What are the losses are coming? So if you see uh, around 1930, this is the example I have considered for Bikaner, Rajasthan. Around 1933 kilowatt hour per meter square per year. This is the energy, sun energy is falling on a horizontal surface of 1 meter square in a year. So this data is generally available in from the NASA websites and Meteonom websites. And NASA is maintaining these data like temperature, wind velocity, uh, global horizontal radiations, inclined radiations. They are maintaining the data for last 25, 30 years. So this data is quite accurate because this is the average out of the last 25 years. So for the Bikaner location, so this is the energy which is falling on square meter of area. So this is falling horizontally, but sun travels from east to west throughout the day, and it is never horizontal. So what we do to keep our panels uh, towards sun so that we get the maximum sunlight, we use the solar tracker. So this is the example of solar tracker where from east to west sun is going, and accordingly the solar panel also getting tilted uh, to track uh, to track the position or according to the position of sun. So in that case, what happens? We get the uh, high energy because this energy is falling horizontally. This energy is falling normal to solar panel. When we track it, so we are always getting the normal power. Sunlight always normal to panels. So there is an increase of around 22.5%, around 22, 23% increase is there once we track the sun. If you don't track the sun, we'll get the 1933 kilowatt hour per meter square. But if you track the sun, we'll get around 2368 kilowatt hour. So this energy is falling on solar panels. But what happens? My panel may not be clean. They may have some soiling. There may be some soiling on the panels. Uh, Whatever sunlight is falling on the panel will not get converted to electricity. Something may get reflected also, and there will be some shading effect also, like in between panels. panels may cast their shadow on nearby panels. So if we assume all these losses like soiling of panels, reflection, shading, so this comes to around 7.4, 7.5% losses we can account. So after accounting this much losses, what we find that around this much uh, 2192 uh, kilowatt hour of energy reaches the solar panel on the top of the solar panels. But now our solar panels are having the efficiency of 20, 21, 22%, because we have seen earlier, like cell has efficiency of 20 to 23%. So whatever sunlight is falling, so 2192 sunlight is falling on solar panels, so full will not get converted to the electricity. So what will get converted to the electricity depends on the efficiency of the panel. So only 21% of this energy will be converted to electricity. So which comes to around 487 kilowatt hour. This is the efficiency of the front side. But nowadays the panels are coming like from the back side also they generate the power. So this increases the efficiency of the panel. So if we take both the generation, means from the top as well as from the back side, the output which comes out from the solar panel is around 487 kilowatt hour per meter square. So this is the basically power which we'll get from the in the Bikaner location. But this is in terms of the meter square. Suppose we take a live example, which is actually this plant is already there in the Bikaner. If we take the live example, uh, in the live example, there is a solar plant capacity 341 megawatt DC. This is a 250 megawatt AC power plant, and DC capacity is 341. So what is happening? Uh, these panels, this much panels, 341 megawatt solar panels, covers area of around 16 lakh 29,128 meter square. So this much area is being uh, covered, or this sunlight, this much area is a solar panel area. Now we know from the this above that around 487 kilowatt hour per meter square per year is coming from the panel, and this is the solar panel area. So if you multiply both, so what we will get, actually we will get the electrical energy coming out from the all panels, means 341 megawatt panels will generate this much electricity per annum. So this is how much electrical energy. This is around 793 million units electricity will be generated. So 793 million units of electricity will be generated from the solar plant of 341 megawatt. So this is the energy which is at the panel outside of output of the panels. So at this point, this much energy is coming. So, but what will happen? From panel to grid, there are a lot of electrical equipments are there. So, a lot of losses will happen. So, that losses comes to around 20%. So, that loss comes in which form? Basically, temperature. Because when we talk about the Bikaner, the temperature is also very high. Sometimes the temperature goes as high as 49, 50 degree. So this will reduce my uh, generation. So that accounts for around 9% on yearly basis, on averagely yearly basis. Further, there is a ohmic loss because there is a DC cables, there is a AC cable, so they have their own losses. So that loss accounts for around 2%. Further, there is a module mismatch. Like two panels are not of same capacity, same rating, same uh, they don't generate same current also. And we know that if in series, there are four, suppose three panels are connected, and each is having the different current generation. So, and but being in series, only one current can flow. So the lowest current will decide the uh, which current will flow in the uh, that particular series. So that is called the module mismatch. So that also counts for around 1%. Then after that, there will be the equipment efficiency. Like inverter has 99% efficiency, and transformer has similar efficiency. Switchgear panels. So all these panels, those equipment losses is around 3%. The next factor is auxiliary consumptions, because you uh, have the power plant, so you will be using for auxiliary load will be there, like SCADA load will be there, your AC load will be there, your lighting load will be there. So all those losses also you have to account for. Further, there may be system unavailability. Like in a year, you cannot certain that my plant will be available for the full uh, full sun hours. There may be sometimes uh, inverter failure. There may be sometimes transformer failures. There may be sometimes earthing defects. So considering that around 2% is the system unavailability, and sometimes grid may not be there. So considering that all factors is around 2%. And if we account all these losses, that comes to 20%. So what is happening? Solar out from the solar panels, this much energy was generated, which is around 800 million unit. 20% get lost in these losses. So ultimately, how much energy we get? We get around 644 million unit of electricity from a solar power plant. So this is the electricity which we get from the 341 megawatt peak power plant. So from this example, if you see what is the utilization factor comes to around 21%, 22%. And a performance ratio, this is the basically the efficiency of the power plant. So efficiency comes to around 81%. So, so, so this is all from my side. Um, I request if you have any queries, please you can uh, ask. And uh, my mail ID I'll share with the Gautam Buddha University. If somebody wants to connect and somebody wants to have some more clarity or some more questions, you can always contact me.
I'll
So,
request. Yes, 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 sir. Yes, sir. Please continue.
yeah, yeah. So this is from my side. So I'll be happy if somebody is having any query or questions.
I'll request all the participants in case of any queries, please ask. Sir, I am having one query.
Yes, ma'am.
Is it possible that, irrespective of series and parallel connection, we can implement some other connections onto our solar panels?
Ma'am, actually, this series parallel combinations which we make to get the desired voltage, because all panels power is going to inverter. So inverter are designed for one
Mhm.
particular input voltage. The
Okay.
input voltage is generally 480 volt, 480
Okay.
or 500 volt.
Mm-hmm.
And my one panel gives the output of around 24 volt.
Okay.
So to make 480 volt input to the inverters, we have
Mm-hmm.
to connect around 22 uh, uh, solar panels in series, so
Okay.
that we will get the desired voltage of around 480 or 500. So series combination is must. We cannot avoid it.
Mm-hmm.
Once we have made the series combinations, it has to be parallel only, because whatever desired voltage is there, we have already got in
Mm-hmm.
24 series combinations. So
Okay.
after that, whatever combination is happening, that is happening the parallel.
Okay. Thank you, sir.
Thank you.
Anybody want to ask any question? Okay, let's proceed with the conclusion of this program. Thank you, sir, for giving us the insights about the Pradhan Mantri Yojana market scenario in India, telling us that more than 50% of our solar power plants are in three states, that is Gujarat, Rajasthan, and Andhra Pradesh. You have also given us the knowledge about the per unit generation of cost of solar. So, at the last, I'll thank you. Uh, and I would like to extend my sincere gratitude to our expert, Mr. Sunil Kumar, for taking his valuable time to be with us today. Now, I'm confident enough that this FDP will be both enlightening and inspiring for all of our participants. Thank you, sir.
Thank you, ma'am. And thank you to all the participants. Thank you.
Okay, sir.
Thank you.
I'd request all the participants, since we will be continuing with our next presenter. So please don't leave the session. We'll start from 4 till 5:30. Thank you. Good afternoon, sir. Am I audible to you?
Yeah, good afternoon, ma'am. This is Rohit Anand. Hope I'm audible.
Okay, yes, sir, you are audible to us. Sir, we'll start at 4 p.m.
Yeah, fine. I will just
Let
checking. Hope I am audible and visible. The presentation is
yeah,
visible to all of you.
yes, sir. Slides are also visible.
Sure.
Your presentation is visible, and you are also audible to us. So let our participants join. We'll start sharply at 4 p.m.
Fine, ma'am. Thank you.
Okay, thank you,
Will
sir.
do.
Good afternoon once again with our respected participants, esteemed colleagues, and distinguished guest, Mr. Rohit Anand. It is my great pleasure to extend a warm and heartfelt welcome to all of you on day 3, session 2 of this faculty development program on emerging trends in battery energy storage system. In this context, today's FDP will provide us with the opportunity to not only gain insights into the latest technological developments, but also to engage in discussions that can help us bridge the gap between research and practical application. Sorry. We are honored to have with us Mr. Rohit Anand. Welcome you, sir.
Hello
He,
everyone. This is Rohit Anand from BHEL.
he
I
is
hope I'm
deputy.
audible, ma'am.
Yes, sir, you are audible to us.
Thank you.
He is Deputy Manager, New and Renewable Energy Business, BHEL, New Delhi. He had completed his BTech in Electronics and Communication from Madan Mohan Malviya Engineering College, Gorakhpur. His expertise includes battery energy storage system, business development, system engineering, and project management. He had executed several sites projects in solar power plants from 2013 till 2017. He was associated with SBI from 2012 till 2013 and BHEL since 2013. Throughout this program, sorry, Mr. Rohit Anand will guide us through the innovations of emerging trends in battery energy storage system. We are sure that your insights will not only inspire us but also empower us to integrate these advancements into our teaching, research, and professional practices. Now, I encourage my all the participants to actively participate during the sessions, ask questions, and foster meaningful discussions. Now, once again, I welcome you, sir, and to take over and guide us during the presentation.
Yeah, thank you, ma'am, and welcome all the participants. This is Rohit Anand, and it's absolutely an honor to just address such a learned gathering. Though I have taken a rounds of sessions in my past 10, 12 years of career with BHEL, but this is the first time I will be taking a session of a faculty development program. So I hope it would all go with the kind of blessings I had with my teachers and my colleagues over here. And in terms of BESS, I will be talking you about the emerging trends in BESS, the industrial insights, and the kind of tenders we are seeing in the market and the kind of requirements which are getting emerged in the market. So I will be just switching on to the full screen. I hope my screen is visible to you all.
Yes, sir, your screen is visible to us.
Right, thank you. And I encourage all the participants, if you have any queries, you just ask me in between the presentation itself. So though Sunil sir had already given you a brief of our BHES expertise, I will just give a small brief to all those participants who have joined in this session itself. So we are India's flagship engineering and manufacturing company. We are operating in diverse mix of product profiles ranging from transmission, transportation, power, defense, renewables, oil and gas. And we have a footprint in over 89 countries with over 200 gigawatt plus installed in India itself and 17 gigawatt contracted abroad. And we have 16 manufacturing units spread across in India, over 28,000 employees and over 9,000 engineers. We have a exhaustive R&D expertise, and we have our R&D center at Corporate R&D Hyderabad, and have a consistently influx of capex into the R&D activities of over 2.5% of our revenue. We have also got 5 research institutes and 15 center of excellences spread across our manufacturing units pan India. Over 5,600 plus IP rights are there with the BHL's portfolio. So this is just a brief of our presence pan India. You can see. Moving on to the topic of the day, it's the energy storage systems. Though I understand that there's already a session by Professor Arun Kumar from IIT Roorkee on energy storage systems, so I won't be going into the deep workings of the battery energy storage system. Rather, we will be focusing on to how it is getting utilized in the industry altogether, the application part of it. And moving on to that, just to give a brief of, though for those definitely who are joined today as a beginner. Its energy storage system is a system which stores energy which can be used at a later point of time. This energy can be coming from maybe a renewable source, be it a solar or a wind energy system, or it can be from our grid also. We store this energy into the batteries or different forms of energy storage systems available, and then utilize it on as per our requirements. So there are different type of energy storage systems available with us, be it mechanical kind, electrical, thermal, or electrochemical. One of the oldest kind of is like the pumped hydro, which is a mechanical kind of an energy storage system, storing the energy in the form of pumping the water onto a higher level, then discharging it down through our turbines and generating the energy. So in this particular session, we will be focusing on to the electrochemical, particularly the battery energy storage system kind of BESS. And moving on to the why do we need battery energy storage systems? As Sunil sir was telling that a huge target is there for India to shift towards the sustainable grid and getting more and more renewable added to the grid. But with the renewable integration, what we understand is like solar, the sun is not shining all the time and wind is not blowing. So whenever there is an intermittency in the grid, intermittency in the supply from these renewable energy sources, the grid may become unstable. So to curtail these intermittencies, we need some source of energy which can curtail or which can ramp up and get in between these transitions. So farming the generation from intermittent sources like wind and solar is one of the key aspect which is bringing this battery energy storage in the limelight in the recent years. In addition to that, the ancillary services for frequency regulation, any changes in the regulation of frequency, deviation settlement mechanism, we will be taking more about it in the coming slides. So these supports will also be provided by battery energy storage systems. Congestion relief in transmission systems, peak shavings, transmission and distribution, upgrade deferrals, and our time tested and old backup hours for power reliabilities. All these will be your applications. So moving on to the India's energy landscape, current energy landscape scenario is something like at present 457 gigawatt hour of energy generating sources are installed in India. This is from the NITI Aayog's website of 30th of November, updated as of 30th November 2024. With that, the fossil fuel base is like 53%, and our non-fossil fuel bases are somewhere around 47%. Out of that, the intermittent solar and wind and a very small percentage of biomass is around 34%, like 154 gigawatt. Now, what National Electricity Plan, this is like Central Electricity Authority of India, had projected the expected generation capacity mix by year 2032. So this 154 gigawatt renewable energy sources today are expected to be 502 gigawatt by 2032. So this is a significant increase if you see, and compared to 243 fossil fuels today, coal, oil, or gas based polluting our energy generating sources, they are just expected to increase to just barely 24 gigawatt. So it is a significant decline from 53 to 32%, and the renewable is expected to be over 50% of the capacity of expected 900 gigawatt actual expected to be there by 2032. Further, in projections for 2047, CA projects this capacity to expand to over 2,000 gigawatt, and over 88% will be from the non-fossil fuel based sources. So keeping in mind on the primary current targets which are already defined by CEA for the 900 gigawatt by 2032, over 50% of that will be from the renewable sources. And just like I told that renewable energy sources being primarily from solar and wind are like intermittent in nature, definitely there is a requirement of battery energy storage systems and pump hydro storage systems to support these intermittent sources. So what NAP projects is like 47 gigawatt by 236 gigawatt hour of battery energy storage systems will be required by 2032. And this is like the projected capacity year over year getting added up. So this is the cumulative capacity by end of 2032. And to enable this kind of installation in India, as of now, if you see at present, hardly out of this 236 gigawatt hour, at present, somewhere around 250 megawatt hour maybe like 0.25 gigawatt hour kind of capacity is installed, 0.3 gigawatt hour. So this is a very huge inclination if you see. So to aid that and to promote this kind of addition of battery energy storage system into the grid, this Ministry of Power had brought the viability gap funding scheme. This is a AGF scheme which gives the support of like an initial outlay of 3,760 crores for the development of initial 4 gigawatt of BESS projects. And in addition, on the previous years, like some other enablers have also been given by government, like National Framework for Promoting Energy Storage Systems. National Framework for Promoting Energy Storage Systems gives the guidelines to all the states wherein they are advised to incorporate as many battery energy storage system plants with the upcoming solar and renewable power plants, other renewable plants, be it wind. And energy storage system also got inducted into the harmonized master list of infrastructures in 2022. So getting this added into the harmonized master list into the energy segment, what it gives like the banks or like the bigger lending agencies, they can also invest their monies or they will give the fundings to the loans to all the developers and this energy power plant developers to bring better energy storage system into the grid. So this opens an avenue for the developers to inculcate BESS also into their generating sources. Then there are ancillary service regulations by CRC in 2022, which clarifies like the BESS can also be taken into the ancillary services and it will also be paid accordingly. So these kind of clarifications were given. Guidelines for procurement and utilization of battery energy storage systems were given by MOP Ministry of Power in 2022. They are something like what kind of tenders to be floated by the employers being like Solar Energy Corporation of India, NTPC, or the state discoms. So it gives the guidelines like the minimum capacity should be somewhere around 100 megawatt, or the timeline should be around 18 months to 24 months. These kind of things were specified. What would be the payment ways? What would be the LDs and penalties? So those things were clarified. These things are the standardization which are already enabling more and more tenders to getting materialized in the years beyond 2022. I will just showcase these things to you. And waiver of ISTS, interstate transmission charges, on battery energy storage charging. If a battery energy storage system is getting charged from renewable energy sources, like minimum 80% of the capacity is getting charged, then the interstate transmission charges or the wheeling charges on the electricity pulled from another point to the battery energy storage system will be waived off. And then it's to be gradually incorporated year over year beyond 2025. This was in 2021, and hope few more relaxations will already be there, or that MOP will be working on it. Then moving on to like what BHEL is doing in battery energy storage systems. So we offer concept to commissioning, like we are into like EPC, engineering, procurement, and construction company. We make power plants, we make nuclear, thermal, solar, hydro, floating solar, all sorts of power plants. In addition to that, battery energy storage system also, we are giving the EPC services where we do the complete concept to commission design, procurement of material, erection and commissioning at site, operational maintenance if required as per the contract agreements. And we are capable of providing all sorts of application kind of, be it peak shaving, energy time shifting, PV smoothing, frequency regulations, to any sorts of BSS requirements. We offer the solutions to that. Completely customized solution can be catered. This is one of our 1 megawatt hour battery energy storage system we designed and developed and commissioned in 2018 itself. 2018 would be somewhere like the start of the battery energy storage systems in India. So we got this project in somewhere around 2016 and 17, and then it was commissioned in 2018. It comprises of a 500 kilowatt hour lithium-ion battery energy storage system in a 40 feet container, a 300 kilowatt hour advanced lead carbon based batteries in a 30 feet container, and a 200 kilowatt hour flow batteries in a 20 feet containers. In addition to that, we have also commissioned this system is like a this system was developed at R&D Hyderabad. It was also connected to the solar, and this system was planned to somewhere like how the battery lithium-ion batteries would work around for the different kind of applications it is intended to, when we are charging it from the grid and utilizing for like solar PV smoothing, ramp rate controls, and energy time shifting. And similarly for the flow batteries also were very new at that time. So we had installed this 200 kilowatt of flow as well. These systems are functioning and are giving their regular data to our R&D team members there. Accordingly, we are just strengthening and designing our current system for the requirements. In addition to that, we had also commissioned a 410 kilowatt hour battery energy storage system in Delhi, which is catering to different applications. Applications in the sense like the system which is this 230 kilowatt system installed at the one of what we can say a power substation at one of our locality, which caters to the overload management of distribution transformers there. In like a new French colony is there in New Delhi, wherein the local power supplying electricity boards substation is there. Therein, if in some months when summers are there, there is a peak of power requirements for some hours only. So to cater that, a battery energy storage system has been deployed to cater those seasonal peaks. Then again, in the Dwarka segment, this is a residential society where we are catering the critical loads of lift and their water pumps during any power outages, and this also mitigating their DG requirements to the society. So this is sort of a DG replacement and catering to their critical loads. Then one of their this Vasant Coach, we are doing the time of day based tariff, like we are charging it from the solar when their excess solar is available, the existing solar at the customer's facility, we charge it from that and discharge it during the non-solar hours when the peak hour rates are high. Apart from these, BHL has also got a state-of-art facility for packaging and testing space-grade lithium-ion batteries for Indian Space Research Organization applications. We are, for over a decade, we are supplying the solar modules and batteries according to the designs of ISRO for their various satellite and space programs. For the recent Chandrayaan 3 mission also, we supplied the lithium-ion batteries to them. BHEL also set up a spirit-grade lithium-ion cell manufacturing facility. It is a small facility for exclusively developing cells right from the scratch to the ISRO application specifically. And this is an internal view of the 1 megawatt battery energy storage system at our corporate R&D Hyderabad. These are like the flow bat. This is the lithium-ion battery racks. These is the inside view of the container where the racks are mounted on the two adjacent walls and battery modules are kept inside on each racks. They are connected in series and then connected to the inverters. This is the regular advanced lead carbon batteries. And this is a view of the flow battery based system. Flow batteries got just like in our lithium-ion batteries and lead carbon batteries, they are like somewhat solid batteries or solid state batteries, not solid state, solid batteries. But whereas in flow batteries, the charging or the electrolytes are in liquid form. So vanadium, this is a vanadium redox flow battery based system, wherein the pumping and pumps are there to just to be utilized during the charging and discharging process, wherein the vanadium is transformed from the one tank to the another, changing their balancing states. And this is the power conditioning system. A power conditioning system is something like which converts the battery's DC voltage into AC to discharge it to the grid, or when charging, AC is converted into DC to charge the battery. So BHEL has developed a PCS. This 630 kilowatt PCS is already installed with our 500 kilowatt hour lithium-ion battery based container, and this PCS is already housed inside in this particular container. This configuration was done in 2018. In this container, only like half of the capacity was holding the batteries, and there is a perforated partition in between. The pieces were also housed inside, and a small workstation for the energy management system. In addition to that, BHEL is developing the higher ratings 1.25 megawatt and 2.5 megawatt power conditioning systems for battery energy storage systems. This development is getting done at our engineering, this electronics division at Bangalore. So now moving on to the building blocks of battery energy storage systems. Anyone, if any queries are there, you can just please raise or maybe just interrupt me.
Participants, do you have any query? I'd request all
Or
the participants, if in case you have any query, please ask.
yeah, if you want, you can just also drop it in the chat box. I will just maybe in between just have a look onto that.
Yes. Okay, sir, please continue.
Yeah, sure. Thank you. So these are the building blocks of a battery energy storage system. So primarily, battery energy storage system do not have many parts as we compare it to a thermal power plant or a hydropower plant. Herein, the batteries are housed inside a container. So if you can see, these are the batteries, a batteries and battery management system. These batteries, which I showed you in the previous slide, are housed inside the racks, and a battery management system is there, which monitors its state of charge, state of health, when the batteries are getting high temperature or not. All these are getting monitored by the battery management systems. Then this is completely this battery management system. This batteries are connected to the inverter. Inverter is a power conditioning system which charge or discharge the batteries. It is a bidirectional conversion system, and through this, the batteries are getting charged. Either it can be charged from our, if you can see this, either it can be charged from our solar power plants or can be charged from the grid, as the case may be. And all these systems are in connection with the energy management system. Energy management system, what it do is it communicates between the solar, the site requirements, the load requirements, and the state of charge and discharge of BESS. If there is solar is generating, then what this energy management system will do, it will discharge, discharge to the load through the solar. If the solar is not there, then it will see if batteries are charged, and it will cater the load through the batteries. If batteries are also discharged and load requirement is there, then it may be feeding it through the grid. So that way it will be keep on monitoring all the generating source like solar and available battery energy storage system and grid, and then keep on catering the load requirements. So battery BMS, PCS, EMS, and these battery BMS are housed into a containerized housing. So this containerized housing is also having our liquid or air cooled system to keep the batteries cool, fire alarm and protection systems. Apart from that, our transformers and circuit breakers are there to connect it to the grid. So what these battery energy storage systems are doing it the batteries are need to be kept at a temperature of around 25 degrees centigrade to operate. So that is why they are usually housed in the containers, and with that, as per the capacity inside the container, we put air cooling or the liquid cooling. Currently, if you see, when we started in 2018, a 40 feet container was housing somewhere around 1.5 megawatt hour kind of batteries. Currently, today we are housing 5 megawatt hour in a 20 feet container itself. So a 40 feet container would house 10 megawatt hour kind of batteries. So significant advancement had happened in the battery technologies as well, the kind of sizes, the energy densities, which I hope you have already had in the previous session of yours. So with that, in the industrial application today, we are housing 5 megawatt hour of batteries in a 20 feet container. Whereas to compare it with the solar, a 5 megawatt kind of solar would require somewhere around 15 acres of land. And this is just 20 feet. So it is a very huge contrast in compared to that in the size requirements. This is a view of the India's largest battery energy storage system as of today. This is the Solar Energy Corporation of India's. This is the main customer, and 40 megawatt and 120 megawatt of battery energy storage system at Rajnandgaon, Chhattisgarh. So this is a view. This plant was developed by Tata Power Solar, and this is the exploded view. If you can see from the top, there are these 20 feet containers are stacked around, and these containers are opening towards the outside. Not the earlier what I was showing you. There is a pathway in between to walk around that have been now omitted to stack more batteries to make the density even higher for a container. So all these containers are openable outside and addressable for all their service and repairs. This is like a 20 feet containers which they have used. These containers are housing batteries only. These batteries are getting connected to this. If you can see this equipment, this is the PCS, power conditioning system, which is catering the charging and discharging of these batteries. And apart from that, then it is going to this PCS is converting the DC to AC. AC is going to the transformers, stepped up to the required AC voltage levels of 33 kV here. And then through the grid, it is through the switchyard, it is getting connected to the grid transmission lines. Now, if you talk about the applications of energy storage systems, so charging and like charging our batteries and utilizing when power is not there, just like we do in our houses, that is like the most basic or the most primitive application which we can have with our batteries. Apart from that, there is like load leveling. Load leveling is something like, if you see, this is the load curve of your some locality somewhere. You see there is a peak in the morning and a peak in the evening, and down, and low peak regions are there in the rest of the day. So what we can do, we can deploy a battery which will be getting charged when the load levels are low and getting discharged when the peaks are high. So load leveling involves storing power during period of light loading of the system and delivering it during high demands. So what is doing is actually, if you see that this demand is will remain like this for another 1 or 2 years, maybe not definitely 1 or 2 years, for some more time. So you will be like postponing the environment's investment into more generating capacity. If you deploy another generating capacity here, like another thermal power plant or a solar power plant, what it would do, it will be meeting these peaks, but then again you will be having more surplus in off peak hours. So these kind of requirements can be deferred using battery energy storage systems. This is an application of load leveling. Another is like this peak shaving, wherein instead of just addressing the maximum of whatever is available, you are just catering to the peaks. This is usually what we see in the industrial load applications in the industries like any automobile manufacturing industries or another cable, cements. So wherein what they have is like peak hours are there for the industrial customers. In peak hours, they have higher tariff rates. So what they do is they deploy a battery energy storage system to meet their requirement of 1 or 2 hours in the evening where the peak rates are there. So they will just charge the batteries during their non-peak hours. Same can be done for non-solar, this peak from non-solar hours also. Sorry, peak, you can charge it from the solar also or non-peak hours in another grid connected systems, and then utilize these batteries in the peak hours. So with that also you can just optimize your expenses. Another application is like power quality. So what is happening is like if you have any very critical or like very sensitive loads connected to the grid, so you can incorporate a battery energy storage system, since BSS have a very fast response time. So if any drop in the cycles are there, so it will just switch on and supply, and it will just make the system healthy. Just like in our healthcare system, this is one of our critical requirements, or wherein like we draw cables in industries, they do not want any jerk in there, any change in the thickness or length or protrusion extensions. So there they can deploy these kind of battery energy storage systems. Then frequency regulations is there. Frequency regulation is like any variation in the frequency. So that can also be catered with the battery energy storage system, wherein if any excess frequency is there, it will charge, battery will absorb that and start charging. And if any drop in frequency, then battery will start discharging, and then it will stabilize the frequency. Similarly, capacity firming, what I was talking earlier, like the intermittent nature of renewable power plants. So wherein like any intermittency is there in that, so that can be catered by the battery energy storage system. So if you see, this is, if this central line is our load profile, if we want to supply it like that, if any excess is there, then battery will charge. If any drop in there, small drops are there, then it will keep on charging and discharging on regular basis. This is what is happening on like our moving ahead averaging. It will just keep on averaging the last 10-15 minutes, and accordingly it is the EMS is planning whether, if that level is not there, then it will discharge. If the power is coming below above that level, then it will charge the batteries. So this is capacity firming for our renewable solar and wind. So any like if any cloud cover is coming, so the solar will dip. If a cloud is passing over the solar panel, so the solar generation will dip, then it will just be substantiated by the battery energy storage systems. All these things become more and more important when so much of solar is getting deployed into the grid. Because as of today, any variations in solars may be compensated by the adjacent running thermal power plants. Adjacent in the sense like maybe another 100, 200 kilometers running thermal power plants. It will ramp up and it will just compensate to any variation in the requirements of power and frequencies. But when more and more this intermittent solar and wind is getting deployed into the grid, then these kind of solutions would be definitely required to idealize the grid or grid stability actually. Spinning reserve is another example, or like DG replacements, wherein like critical loads like hotels are there, hospitals are there, or some factories or offices where the critical loads are there, servers, data centers, wherein a DG is running in idle. If any grid outage is there, then DG has to kick in and immediately take the load. Whereas DGs usually take a minute or two or even more to get to their rated capacities. So DGs are getting into idle, and with that they are just exhausting diesel, and they are not very cost optimized. So to those kind of equipment, we can deploy a battery energy storage system, which will just maybe we can size it such a way that for the time being, if our DG takes 1 minute to get to the rated load capacities, so we will put a BSS which will be on a high discharge basis. It will cater the load for the 1 minute or 2 minute, 10 minutes. That way it will work out. So we can just omit spinning reserves. The system can respond in milliseconds to minute and supply power to maintain network continuity while the backup generator is started or brought online. So now I will just, this was the maybe sort of the application which we have seen across. Now coming on to what is the market is seeing today in terms of like battery energy storage system. Just like I was telling you, a one container, we are 20 feet container, we are housing 5 megawatt hour batteries. Our recent largest India has deployed is 120 megawatt hour battery energy storage system at Chhattisgarh, Rajnandgaon. And current tenders are coming up with like a gigawatt kind of battery energy storage tenders. That power is like 200 megawatt slash 500 megawatt hour battery energy storage systems, or 500 megawatt by 1000 megawatt hour. And just to clarify, actually, the battery energy storage systems are getting rated in to megawatt and megawatt hour. So, wherein this, if you just see this NTPCs, this is one of the recent tender which is currently running. So, NTPC requirement is like 100 megawatt hour. 100 megawatt is a power rating, and 400 megawatt hour is battery rating. So, this system will be able to supply 100 megawatt for 4 hours. So, this is a 4-hour battery system. You can supply 100 megawatt hours for a 4 hours. Similarly, another tender is this NGES 25 megawatt by 100 megawatt hour. This is another 4-hour battery backup system. Such tenders are already there, which are like 500 megawatt by 1000 megawatt hour. So, like a 2-hour backup systems are there. They will be catering the system for 2 hours only, but 500 megawatt kind of capacity. 500 megawatt is a really big or good rating. So now coming on to the design life or the kind of requirements we see typically in tenders, these are some of the typical specifications which we see in the tenders. So design life of BSS, this from just going on to the design life, these batteries which we were talking about, lithium-ion batteries primarily we are focusing here, and they are having a cycle life of 4,000 to 6,000 to 8,000 cycles. Cycles is like being like charging and getting, you charge the battery and discharge the battery. That is one cycle for a battery energy storage system, this lithium-ion batteries. So 4,000 cycles amounts to like 10 years of life, and 8,000 cycles is like 20 years of life. Whereas using those 8,000 cycles, if you charge and discharge the battery 2 times a day, then you will be exhausting those batteries in 10 years itself. So the design life of BSS are ranging from 10 years to 20 years. Battery technology agnostic, you can put any kind of batteries. The number of cycle requirements are like either 1 or 2 charge discharge cycles per day. Power to energy ratio maybe it can be 1:2 or 1:4. These are the example of 1:4. 1:2 maybe like somewhere around 500 by 1000 megawatt hour. Then year over year dispatchable capacities. Now, since these batteries degrades, just like in our mobile batteries or our home inverter batteries, these degrades over time. When we utilize these batteries, so the initial year they will be giving you, the system will give you 100 megawatt for 4 hours. But with this annual degradation, when we utilize these batteries, it will not be able to give you 100 megawatt capacity for 4 hours for the 10th year itself. So there are different kind of tenders. Some may ask like, you give me this capacity at the end of 10th year also. So then you have to accordingly oversize your batteries. Some may ask, okay, we have given a annual degradation, accordingly you size your system. Some may say, okay, the bidder can design his own system and you specify as to what will be your discharge, but it should be in the rated discharge allowed in the tender itself. Then there can be the degradation. Degradation can be specified by tender or it can be in bidder's purview, but it should be in the within a permissible limit. You cannot say that my system is will be able to deliver only for 5 years. So The thing is like you will be putting a battery energy storage system in a customer space. He has to charge and discharge. So those batteries has to be efficient also. If I put 100 units in it, it should give me 80 units out of it. It should not be having an efficiency maybe like lower than 80%. Either I will be putting 100 and it will be just giving me 60 units, and it is a non-efficient system compared to someone else for that same amount or maybe some slightly more amount. So when you see this for a very long period of time, 10 years, 20 years, so that makes a lot of money. So to curtail that, like usually tender specifies that minimum AC to AC round trip efficiency. Maybe it has to be like 80%. 80% is like our usual standard in the market as of now. Some tenders are now moving on to like 80%, 85%, 86% for some years, then a degradation in the efficiency as well. Currently, we can take like more than 80%. The battery energy storage system should be efficient in the initial year. Applications, just again, like I told you, all kind of different applications may be there. Then response time, availability, the system should be available 95% of the time. So what does it mean? Like whenever the system is called to discharge, it should be able to discharge. It should not happen like the system is not able to perform. So if those things are there, then there will be penalties. Penalties are there on availability. Penalties are there if efficiency is low. Penalties are there if you commission this system. If a tender is asking to commission this system in like 15 months or 18 months, then you have to commit that. Otherwise, there will be penalties on delay on commissioning. DOD is like depth of discharge. Depth of discharge you may have heard in terms of batteries, like a battery capacity, if it is say 100%, then you can discharge it to some level. Maybe you have to leave another limited 10% at the end to maintain its state of health or do not over deplete it. We should not over deplete. So a depth of discharge is there identified. So minimum like 90% DOD is like customer. My battery should be able to discharge 90% at least. The BSS charging like when just like I told, there are different kind of tenders there. Some tenders like very few are there now who say you deploy a BSS, charge it on your own, and then just give me the power. Usually more are like I just need a battery energy storage system of say this capacity, 100 megawatt, 400 megawatt. I will charge it and I will discharge. So charging and discharging will be in my purview. You need not to worry about the charging power. So that kind of different models are there. Accordingly, we have to size our system and build our prices while quoting into the real world scenarios. This is a tracker. This is like a information about the kind of tenders which we have seen or the capacity additions which we have seen into the battery energy storage system. So if you see here 2018 onwards, like these many megawatts, these many gigawatt kind of tenders were floated. So initially, in the very initial year, there was a very limited tenders because the industry was apprehensive whether the system will perform or not. The costs were high. Then in 2022, that guidelines were there in place, and battery prices were started declining after the post-COVID era. Then the tenders will keep on increasing. The capacities were also getting increased. So if you see like in 2022, maybe like 10 gigawatt kind of tenders got annulled out of 14, whereas in 2024, the last year had seen a very bright year for battery energy storage systems, wherein like over 14 gigawatt got awarded, 12 gigawatt is biddings are closed and are in the technical evaluation stage. 3 gigawatt is already under construction, and 1 gigawatt notice inviting tenders are already there out. So if you see like in terms of like BESS, around 26 gigawatt got in different stages, wherein some got annulled, some got cancelled also. Awarded is 11.8. Operational is like 0.36 in that 120 gigawatt, 120 megawatt. NTPC Rajnandgaon is there. Another is 57 megawatt hour at our KLT, Kutch Lignite thermal station at our Kutch, Gujarat. That is our second largest as of now. Another big projects are already in the execution stage and it should be commissioned like in another 6 to 8 months. One in our local nearby is like in Delhi actually, 110 megawatt is there, which was done by Fluence in 2018, and another 40 megawatt is getting installed for BRPL, which is likely to be getting ready by another 3 to 4 months. So this is just giving you an impression of like how the battery energy storage system is doing. And this capacity, if you see 35, we are talking about 236 gigawatt hour in 2032 cumulative installed. This is giving an emerging trends in the models which are getting deployed into the battery energy storage system tenders. Earlier tenders were coming in like standalone. Standalone in the sense the battery energy storage system is to be deployed, or then it came with like solar. Okay, you club it with a solar. Then something came up with like this firm and dispatchable renewable energy FDRE tenders, wherein like, and these are mainly developer mode kind of tenders. Just to give a idea, two kind of requirements are generating in market. One is like EPC based, which was the usual trend, wherein like if you are a customer, you will pay me the money. I will like you will award me a tender. I will deploy a system. Then you will pay me the money, and I will be out of that. If O&M is there, then I will be doing the O&M, and then you will be paying me on regular basis. However, all my supplies, installation, commissioning, those payments will be paid to me upfront when the system is commissioned. In developer mode kind of requirements, what is happening is you say I do not want the system, I just want the power out of it. So you'd say ki, what you will tell me ki you deploy, you put a system on your own land, you will not be given even the land to me. You'd say you put it anywhere in India, deploy a system, you connect it to the grid, just give me 100 megawatt or 500 megawatt of power on daily basis, one cycle per day or two cycle per day. 500 megawatt, two cycle per day I will want from you. You just give me the quote for that price itself. So that kind of tenders are like energy storage systems as service, energy as a service kind of model it is shifting to. Right from EPC, where the customer is owning the projects, it is moving on to the energy as a service. They do not want to own the system. They just want the energies out of it. They will just have a back-to-back agreement from you that they will buy you from this power purchase agreement rate at this rate, then they will sell it to their buyers like state discoms or big industries onto their agreed rates. So that agreement they make, accordingly these things are worked out. These things are like picking up on a very fast pace, and these are like the one of the emerging trends what you can see in happening in the solar also, or in all sorts of things here in the power generating segment. Kindly make a note that BSS is not generating anything, it is just storing and delivering at a later point of time. So in the FDRE also there is like assured peak. Assured peak is something like he will be, the developer will be discharging it in the peak hours on regular basis, and you will be paid out of it. So this system, this particular format is getting very popular in 2024, and it has seen 10 gigawatts kind of tenders already announced, out of which in different stages something like awarded already 6 gigawatt, very few less cancellation, and 2.4 gigawatt already in construction phase. Then load following is something like developer will say 15 minutes interval he will identify and tell you. Then accordingly you have to just discharge into those 15 minute intervals. Round the clock is like in round the clock there will be solar, and also into some off peak non-solar hours you have to discharge from the batteries. That will be there. These models were there, but they got more shifted towards this particular segment. Then there were again solar and BSS also, different kind of models got explored. So crux is like system is shifting from EPC to developer mode kind of requirements, and in developer mode also FDRE, from dispatchable renewable energy, assured peak kind of model. Coming on to the prices, if we see, so this is the price trend of our solar plus battery energy storage system tenders, wherein in 2018 is when NNC nearly lignite corporations 2018 it saw a price of like 7 rupees per kilowatt hour, or which may be amounting to like 7 crores per megawatt hour, which has come down to a recent of 3.4 in SECIs in this is March of 2024, and in September it has come down to 3.09 rupees only. So this is a system. This NHPC system is like 1200 megawatt of solar capacity. With that 1200 megawatt hour of battery energy storage system is to be deployed. This system will give you this system will supply you power at 3.09 rupees. So this is comparison to what Sunil sir was telling in the earlier session, like solar is giving a price of 2.6, 2.5 rupees, 2.7 rupees per kilowatt hour. With that, this will be the price of this solar, let us say, and from these batteries in this system will supply for 2 hours actually here, this 200, and for including that price, it is coming at 3.09 rupees per kilowatt hour. And this is like 2018 just got saw 121, then there was nothing in 22, 23. 24 saw some significant good amount of responses coming into the market. This is a solar plus BSS. Now this is another standalone kind of requirement. So standalone is something like there is only a battery energy storage system deployed. So here if you see earlier in 2022, the prices were as high as 11.25 rupees, 10.8, like 11 crores, 10 crores per megawatt hour if we compare it to, oh my bad, this is like a lakh per megawatt per month kind of prices. This is like the prices wherein you will be deploying the system. I will just charge and discharge. So you just give me the parking charges. What will be your charges of energy storage utilization, capacity utilization charges? So these tenders got annulled, and recently this has seen a drop with the declining prices of batteries. And with that VGF, what I was telling you earlier, that MOP has announced, with that, the prices have further declined from 3.81 lakh rupees per megawatt per month to 2.37, 2.26. This is the latest one. RVUNL, which saw a tariff of rupees 2.21 lakh rupees per megawatt per month only. There's a VGF of like 30%. Whatever you will be deploying, 30% of that will be funded to you by government under the VGF scheme. In terms of FDRE tenders, what I was telling you earlier. So this is the price trend which we have seen in the 2024 different tenders. This one exclusion, actually, this is primarily because it has got a different kind of requirement, wherein the developer has to deploy the system, charge it from the renewables only, and he has to arrange the power for charging as well. That is why the tender capacity was 2 gigawatt hour. However, awarded was only 200. It had not seen much participation, so we can just exclude the this particular one. And if you see, the price trends are coming around 4.25 rupees per kilowatt hour for the battery energy storage systems in FDRE format. Now, with that, now moving on to the what will be the future of this energy storage systems in India, we see. If we see the kind of solar which we are having today, putting onto the BSS, they will be able to cater the kind of intermittencies they would be generating. But when we are keep on adding the solar so much more, and we would want to shift from fossil fuel based or thermal power plants to renewable only, then we may need to charge the batteries and utilize during the non-solar hours also. So we may need like long duration storage, which will last from the our night 8 to 10 hours, 10 hours, 12 hours actually. For that kind of requirements, we need long duration energy storage systems. So battery energy storage system can reasonably handle the variability of renewable energy power for short durations today. But this is the standing today actually, or maybe the couple of years down the line. But while with scaling up of renewable integration, if we keep on doing this, keeping our targets for 2047 in mind, so the long duration energy storage systems can play the pivotal role to address the transition challenges. Now, just give me a second.
Hello. Sir, do you find any issue?
No, I'm nothing. I'm just drinking water. Just give me a minute.
Sorry.
No, I'm no issue. Just taking a sip of water. Just give me a
Okay,
minute.
okay, no issues. Please have it. Okay, 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 sir.
Yeah, right. So just like I told you, for the long duration energy storage systems, currently we are primarily dealing in like lithium ion batteries. We, in the sense, like the market is dealing in lithium ion batteries. It is getting so much popular that even our government is also incentivizing industries to deploy as many manufacturing facilities in India itself. China is leading at the moment, and that is also primarily because the main element, the lithium which is required China is also taking control of the lithium mines globally. So with that, China is leading at the moment, and in terms of installed capacity, somewhere around 900 gigawatt our annual production capacity India, China is having at the moment. India, as of now, no one is making lithium ion batteries on industrial scale. Our lead battery manufacturers, be it like Exide, Amar Raja, they are deploying their facilities, which are expected to be ready by end of maybe like by end of March 2025. They are already in installation phase. I cannot comment on what is their timelines, but they are under deployment and will be ready as soon as possible. So with that, Amaraja is Exide is deploying somewhere around 12 gigawatt hour. TVS Lucas is deploying around 9 gigawatt hour kind of facilities. 1 gigawatt hour by RE plus. Next charge is there. They are also deploying 2 gigawatt hour. So many are there. They are in development phase in India at the moment. Apart from that, government has also announced the ACC advanced cell chemistry performance linked scheme. Actually, with that, our Ola Electric, which you may be already aware of, they are also deploying a 20 gigawatt hour of lithium ion cell manufacturing facility in India. Reliance is deploying a 5 gigawatt hour, 20 gigawatt hour for Ola, 5 gigawatt hour for Reliance, and 5 gigawatt hour another Rajesh Exports is there. So 30 gigawatt hour with that. Apart from that, so many other which I told you. So India is also ramping up their production facility, just like they did it for the solar modules also. So that would be definitely required if you would want to address the market the pace which we are showing. So that will be more primarily on the lithium and battery front. Now, just like I told for this long duration energy storage systems, there would be different solutions available for that also. Be it electrochemical flow batteries, just like I told in the initial stage, we deployed this flow battery system there in 2018. These kind of batteries have a life of 20 years, 25 years without any degradation, and they will be very good examples for long duration energy storage system. Similarly, there are sodium sulfur batteries are there. Pumped hydro is our old time industry. Compressed air energy storage systems are there. Gravity based energy storage systems are there. They are the mechanical fronts. Thermal is like there are heat. The energy is stored in the form of molten salt, heating, and with the temperature variation, we are utilizing the stored energy. Hydrogen is also another upcoming area. So different kind of long duration energy storage systems are available. Let us see what will come, and definitely all these have their different advantage and segments where they lead. When we say long duration energy storage system, we are primarily talking about over 6 hours kind of storage systems, where lithium ion is more suitable for less than 4 hours or 4 up to 4 hours only, in terms of cost, which we are going to be getting deployed, the kind of life we expect from it. So LDS landscape in India and future prospects. GUVNL is like a Gujarat Urja Vikas Nigam Limited is drafting a tender for 200 megawatt by 1600 megawatt hour, like 8 hour kind of backup system will be that. NTPC is also exploring this long duration energy storage system solutions. And central government has also notified that they may be working on to some guidelines to bring long duration energy storage system into the market. Just with all that good things, just another some couple of things wherein like battery energy storage systems need some kind of working on. The requirement is like the battery safety and disposable challenges. What we see, I told you, so many tenders are already in pipeline getting deployed with 10 years, 20 years of life. But what would happen with those batteries after their life are over, like 10 years, 15 years down the line? So that these are like hazardous material lithium, so they cannot be discarded just like that. Also, definitely we need some standard disposable guidelines for that. Our BIS is already working on to those standards and for safety and disposal. Recycling is another good alternative, definitely, because if we can recycle these batteries, just like our lead acid batteries, where like as high as 95% of the raw material we can extract from it. Similarly, for lithium and batteries, we can also work out on recycling, and we can definitely improve this process is already there. Definitely it's not so efficient because so much of batteries were not getting recycled, not much of capital was invested into it, not much of R&D in terms of industrial level was not done. So this thing is also picking up in recycling at present. Like Loham is there in India, which is also doing a really good work in terms of recycling of batteries. This is another segment which needs further improvement into the lithium-ion battery this cycle. Apart from that, circular economy is like that reusing these batteries from EV batteries which are getting deployed into the electric vehicles. They are like further higher rated batteries compared to the stationary energy storage system which I was talking to you as of now. So we can utilize the EV batteries into our second life kind of applications. Apart from that, we can just extract the raw materials from it and use that again to make fresh batteries out of it. That kind of things to make a circular economy is what the market should be much more focus is to be required onto that segment. So coming on to my last slide is like the what would be the future outlook. Just like I had just this is just a brief of all what I just told you as of now. The growing demand actually the 236 gigawatt hour which is already in place and definitely the 500 gigawatt of which is driven by the 500 gigawatt renewable targets. And if you see renewable is very significant that people like our ministries are even our honorable prime minister has time and again has spoken about it. So definitely renewable is coming big time, and with that the requirement of BSS is also very much sealed with that. So definitely a huge demand is there in this segment. Advancement is just like I told you earlier in a 40 feet container we were putting like 1.5 megawatt hour. Now as of today itself 20 feet container we are putting more than 5 megawatt hour, and the prices have also seen a significant decline. I could not show a slide actually, I just maybe missed it. So prices if we talk about in 2022 we were seeing like $150 per kilowatt hour or even more $200 per kilowatt hour kind of prices. Today we are talking about if we buy bulk in the sense like 500 megawatt hour kind of batteries you buy from China, you are getting it as low as like $60 per kilowatt hour. So it is very significantly low. $60 per kilowatt hour amounts to like 60 to 48, like maybe like 50 lakhs. 50 lakhs for a 1 megawatt hour kind of batteries. Just like when Sunil sir was telling for this solar reference, a 1 megawatt of solar is amounting to 3 crores. So this is like for the batteries only, like 50 lakhs only. With that, you can just add on to your auxiliaries, the HVAC, FFS, and the PCS, transformers, breakers. You can develop a system. The current prices in the market running somewhere around 2.5 crores per megawatt hour when we talk about these systems. And in terms of, so definitely technical advancements will further add more batteries to the containers and definitely reduce the prices. Integration with smart grids. The grids will be also made much more responsive to curtail these intermittencies of renewable plants actually. And even much more like our state load dispatch centers actually SDLCs will be having much more robust EMS which will be able to optimize the kind of load sourcing from where the power will be sourced. It will be from maybe this particular arm of the renewable or from the BSS that will be there. And apart from that, diverse applications, just like I told, different kind of applications can be catered by BSS, and with that, different kinds of price modelings can be done. So with the same system, if we cater maybe like 2-3 cycles per day, and we cater to different kind of application use cases, maybe we would be able to generate much more revenue on the installed BSS. So that will also add more value to the BSS segment itself altogether. So I hope that would be all from my side. Anything is there, you can just please ask me. Thank you. Thank you for your patience and the time already.
Thank you,
Thank
sir.
you for me.
Now I would request the participants in case you have any queries.
No, ma'am.
Thank you, sir. I hope nobody's having any query. Thank you for explaining us. Yes, anybody want to ask something? Okay. Yes, thank you for explaining us and giving us the insights and the knowledge about the battery management system, building blocks of BESS. Now, once again, I would like to extend my sincere gratitude to our expert, Mr. Rohit Anand, for taking his valuable time and be with us today. I am confident enough that this FDP will be both enlightening and inspiring for each one of us. Thank you, sir.
वो कर लिया था आपने माइक
Okay, thank you everyone. Just I guess I think we can just leave now. Have a nice day.